Hello guys, welcome back to the channel, and in this video I wanted to talk about something which is very reminiscent of a video I made in the past called Proof of the Most Beautiful Equation in Mathematics. That video right here is where I meticulously derived Euler's formula, which is a very fascinating thing indeed. Of course, do given more time and experience, I have seen prettier things in mathematics, but still say Euler's formula is definitely up there. But in this video, I wanted to do something very similar, but for a physics concept, which I very recently learned about and which I find incredibly fascinating. And I hope to do it justice by breaking it down in this video in a manner which is very understandable and in a time span for a video that is also quite concise. And that is going to be about the concept of identical particles. Now, identical particles, if you were to think about it classically, if I have two things which are very much identical, then that means that they have similar masses, similar densities, similar like volumes, or for example, if I were to think about two billiard balls, and I'd imagine two balls with the exact same properties, perhaps the only way I can tell them apart is if I color one of them differently, like one billiard ball being red and the other one blue. And actually, as a matter of fact, if I take this classical example and say that I'm shooting these two billiard balls at an angle and place two detectors at the other, you could say, sides of this angle at which I'm shooting them at, then I can imagine two things happening. If I'm shooting, for example, the red one here and the blue one here, well, if I picture that scattering process, two things can happen. Either the blue ball goes to the detector right there as it kind of bounces off of the red one, or the blue ball kind of bounces off of it and ends up in the other detector. And same thing for the red ball as well. This is two outcomes which are kind of different because you know exactly that at one detector the red ball was received or the blue ball was received, and the same thing goes for the other detector, so you know exactly which ball went where. But actually, when it comes to identical particles in quantum mechanics, this is not the case at all. You really cannot tell which particle went where, and this has typically to do with the mathematical description one has for quantum mechanics. Now, of course, in this video, I do not expect you to kind of have a whole plethora of quantum mechanics under your belt, so I'll try to explain everything as much as I can and as simple as I can. For quantum mechanics, the information of a quantum mechanical system is described typically by this mathematical thing, this function called the Schrödinger wave function. It has the information about everything regarding a quantum mechanical system, like a particle, which you're interested in. If we have two identical particles, you can have one general wave function which describes both particles. And if, for example, we're interested in the coordinate of position of said particle, then my overall wave function is dependent on the position r1, which kind of tells you something about one of the balls, and the position r2, which kind of tells you something about the other, well, not ball, but the other electron or particle in this case. So an analogy I heard for the wave function for quantum mechanics was really clever by my professor, is that you can think of the wave function as like if I have a car, the machinery of what is happening inside the car, like the engines and everything that is doing the work, all of those things are kind of oblivious for a lot of you typical users of a car or owners of a car, unless you really know a thing or two about your car. You tend to ignore what is happening under the hood, and what you're mainly preoccupied with is that the car is actually working. Does it have enough fuel, and does it run? Those are the two things which really matters. And the running and does it have enough fuel is the actual observable which you care about the car. Now, in quantum mechanics, the wave function is all of the machinery under the hood, or a more even accurate representation of this is if you're into computer science programming, the wave function is the software, and the basically the observables which you can get from your quantum mechanical system, such as your exact position, their exact total energy, their exact momentum, etc. The things you measure experimentally is the hardware basically of your computer. So I take whichever analogy you want and run with it. The way you get the actual experimental observables from this abstract wave function is by taking the modulus square of the thing. So if you do that, then if you have a wave function generally describing two identical particle systems, then you get some probability for having observed for a certain configuration basically of the states at which your two particles can be in. However, what happens if I reverse the order at which I make the dependence of this general wave function? So instead of the wave function depending on R1 and R2, it now depends on R2 and R1. So in a sense of the way, you're looking at the other particle first and then, so the second particle first and then the first one. Then if you reverse the order, when you take the modulus square of the thing, you actually get the same probabilities actually. So in a sense of the way, the order of this dependence of this general wave function on R1 and R2 really doesn't matter. So what it is telling you is that the way at which you tack one of your particles, if you were able to even, but the matter at which, if you were to speak of this classically, you color your billiard balls, like let this one be a blue ball and let this one be a red ball or vice versa, really doesn't matter because the probability of getting the things at a certain position is just equal, regardless of the tagging. And this is interesting because it tells you basically that you can have two types of general wave function. The two types of general wave function which you can have is one wave function that is totally anti-symmetric, and that is basically that if I have some general wave function psi dependent on R1 and R2, then that is equal to minus the wave function of R2 and R1. So it is minus the one when you flip the sign. And you can have a totally symmetric wave function at which psi R1, R2 is exactly the same as psi R2 and R1. This having two possibilities comes purely from something like taking the square root of both sides of this modulus squared and seeing what you get out of that. But again, that it's just a little bit of mathematics aside. But now one last piece of the puzzle is that from seeing that I can have basically psi R1, R2 kind of be equal to plus or minus psi R2, R1, depending if the thing is anti-symmetric or symmetric, I can actually express this general wave function as some sort of linear combination of psi R1 times psi R2 plus or minus psi R2 times psi R1. This particular permutation of things has a little bit more mathematical nuance to it. It has to do with being able to express things in quantum mechanics in terms of linear combinations. If you're not comfortable with the way at which I formalized that, you can check out this really good video by Part G, a much bigger channel than mine, which really talked and explained this concept really well, I personally believe. But if you're okay with going with this notion that you can kind of grab the general wave function and write it as a more fleshed out thing, as I just showed you right now, then some really interesting insights can be provided. And that is basically that if I were to look at the general wave function of a totally anti-symmetric thing, such as, for example, particles known as fermions. These are typically described by these totally anti-symmetric wave functions because I have psi R1 times psi R2 minus psi R2 and psi R1, and because both terms are pretty much identical, then they equal actually zero if I have two precisely identical particles. And this means that you cannot have fermions be in the exact same quantum states. You can have them be in the same energy level, like you can have them, for example, be, if you were to look in the case of an atom, you can have them be at the same principal quantum number, like n equals 1. But if you know anything, for example, about quantum mechanics in terms of the principal quantum numbers which you can have, or maybe from chemistry, you know that you can have not just the principal quantum numbers, so n equals 1, n equals 2, n equals 3, all of the shells from Bohr's model. You can also have things like the angular momentum quantum number and the magnetic spin quantum number. These different other quantum numbers which kind of have to do with some of the angular dependencies of the electron around a hydrogen nucleus. Now, if I were to have basically two identical particles, two fermions, like an electron in a particular energy level, then to have them be in the same energy level, then the one thing which they should have differently is spin. So, for example, if they have the same energy level n equals 1, if they have the same angular momentum number like L equals 0, so them being in an s orbital, which is like the spherical shaped thing, then the only way at which you can have two fermions fitting on that same kind of energy level is if their spin is different, that other quantum number basically. And in this case, if one of them is spin 1/2, then the other one must be minus spin 1/2. And this is why you get things like the Pauli exclusion principle. You get things like the Pauli exclusion principle telling you that you cannot have these fermions be in the exact same states. Otherwise, you'd have two electrons be in like all of them being in spin up, basically. So one spin up particle and another spin up particle, and that doesn't work because of what we've just saw with the totally antisymmetric like wave function that generally describes this two particle system. You can even extend this further to an n particle system, so it becomes this more giant hot mess, but the philosophy is the same. Now, if you ask yourself what is the case now with bosons, now that is also quite interesting. With bosons, those are typically particles described, as you can imagine, by the totally symmetric wave function. And if I have two identical bosons, where I would have, like, if I were to decompose the general wave function into this linear combination of other wave functions, you can see immediately, if you were to see the equation I just displayed right here, that the psi r1 and psi r2 are going to be added with a psi r2 and times psi r1. So you're going to get a non-zero value, and that basically means that with bosons, you can have them be in the same energy level. And this actually is very interesting because you can have something called Bose condensation. And this is where you have bosons being in the exact same quantum states, like in regards to everything, that they behave collectively as one kind of, you could say, medium, if you'd like. It's a very abstract thing, but they behave as one kind of thing. And perhaps the primary example of this is something known as a Bose-Einstein condensate. This happens, for example, if you grab a helium atom, which consists out of a nucleus that has two nucleons, like two protons, along perhaps with neutrons, of course, as well, and two electrons. If you add the average spin, basically, of the nucleons with the two electrons, then you get an overall spin number, which is an integer spin number. And this means that the helium atom, or certain isotopes of the helium atom, I think helium-4 if I'm not mistaken, behaves like a boson, basically. So if you cool it down to really, really low temperatures, then you can get the helium atom behaving like a Bose-Einstein condensate. And this leads to very interesting experiments with things regarding the field of ultra-cold atom physics, when you want to really study very low energy systems, which would be relevant for studying things in the conditions of astrophysical scenarios or other extremely cold scenarios. So in summary, basically, looking at the two descriptions for identical particles, so you can have the wave function being some totally antisymmetric wave function, in which the realistically describes fermions, which is a huge chunk of the fundamental or elementary particles one has in the standard model, one automatically gets the so-called Pauli exclusion principle, which is very important for physics and chemistry, especially when looking at the ways in which electrons fill the shells in atoms. It helps chemists basically predict the spectroscopic signature one would obtain from various experiments when it comes to various pure elements. So the Pauli exclusion principle is an important concept which can be derived from this notion. And in the case of where you have a totally symmetric wave function which describes boson, one would get Bose condensation being predicted out of the thing, which is also quite fascinating. And in general, I think the really head scratcher is the concept of identical particles being indistinguishable from each other. I still find this to be very bizarre that you cannot really, for any matter of saying or another, kind of tag quantum mechanical systems. Like, they, if they have the exact same properties, then they're going to be completely indistinguishable. So if you have like a sea or a lattice of like electrons, then you cannot technically say that, let's look at electron 1001 right there at that lattice position and electron 90 at that lattice position. You can talk about things in that way, but realistically you really cannot tell which electron is which. Like, it's an amazing thing that kind of is different from classical mechanics, at least in my opinion, as I was studying for the second course in quantum mechanics. I hope you guys found that somewhat interesting and you were able to follow the notion and kind of see the reason why I find this to be so profoundly interesting. And I hope to see you guys again in the future for more content. Stay tuned for more videos, and bye bye.